The NMR Odyssey continues. Now we're going to dive into gory detail on the chemical shift and wrap up, if I don't run too long, with integration. So just to bring you back up to speed from the last mini lecture, when we're talking NMR, we're talking about a nuclear spin flip, energy in the radio frequency range of the electromagnetic spectrum, tiny amount of energy causes NMR active nuclei to flip their magnetic moments. The absorption of energy results in a spectrum, and the important thing is that those nuclei that are in exactly the same kind of electronic environment show up with exactly the same chemical shift. If they're in different electronic environments, they show up with different chemical shifts in different places on the NMR spectrum. And that's summarized in this bullet point. If they're deshielded, they are exposed to the full brunt of the external magnetic field, and they show up on the left side of the spectrum. Downfield, basically it's a higher frequency, larger chemical shift. If they're shielded, protected from that brutal external magnetic field, they are upfield. They show up at a lower frequency, smaller part per million chemical shift, and on the right side. So as I left you hanging with the last mini lecture, what determines this shielding and deshielding stuff? Basically three things. They parallel quite nicely our discussion of acid-base trends way back when in 2301. So we've got electronegativity. The nature of the carbon, that's a little different. Whether it's a methyl, a methylene, or a methine. And the presence or absence of pi bonds plays a pretty big role. This chart here from a previous textbook is a really nice overview of chemical shifts in proton NMR spectroscopy. So plain old alkanes, nothing but methyls and ethyls, sp3 hybridized carbons are way to the right, far upfield, not at all deshielded. Start going a little bit further to the left, it would appear that these pi electrons nearby somehow or other deshield these hydrogens and pulls them downfield a little bit. The impact of electronegativity is very clear right here. If I have an oxygen or a chlorine, maybe a bromine attached to the carbon bearing the hydrogen, boy, that yanks that chemical shift pretty far downfield. It can go as far downfield as 4.5. Starts getting weird around 5 to 8. Doesn't look very deshielded to me, but for some reason hydrogens near an alkene or an aromatic ring are way downfield, and then, geez, oh Pete, you look at carboxylic acids or aldehydes, they're practically off the charts all the way downfield at 10 to 12. This is all wonderfully summarized in yet another correlation chart, which you have in your possession and is, of course, in your book. Let's look at this in some detail. So, what shall we use? How about pink? All right, trend number one. The methyl versus the methylene versus the methine. Note that as you go from the methyl down to the methine, the chemical shift is pulled downfield. This trend is going to hold true no matter what the other impacts are. So, for example, if I have an aromatic ring with a methyl group attached, that shows up at about 2.3. But if it's an aromatic ring with a methylene attached, and I'm wondering, where is this guy going to show up? Well, I see that a methylene appears, let's say roughly about 0.4 parts per million further downfield than the methyl. So I would expect this guy probably is going to show up around 2.7 or so. So that trend is consistent throughout the entire structure. Okay, what else can we look at? Well, how about the trend of our halogens? Chlorine, bromine, iodine. Well, you know that chlorine is more electronegative than bromine, which in turn is more electronegative than iodine. And so it makes sense that this chlorine is pulling electron density away from that carbon. There's a big old bond dipole here. And that's exposing the nucleus to more of the external magnetic field. Therefore, it's a larger delta E spin and a bigger frequency downfield due to that electronegative pull by these electronegative elements. It's really apparent when you have an oxygen nearby. It's pretty much a foregone conclusion that if you have something around 3.8, maybe 3.8 to 4.5, I should say, that's a methyl group or a methylene or a methine adjacent to an oxygen. Okay, and when we're talking about these guys here, notice that we're talking about the carbon bearing the hydrogen is directly attached to an oxygen. Okay, that is completely in contrast to the example for a ketone over here, where a methyl attached to a carbonyl shows up around 2. Methylene would show around 2.4. Methine even further downfield. So get comfortable with your correlation chart. Spend some quality time looking it over. These are fairly reliable values. You can see their ranges. Note that effects are additive. So, in other words, if I have a CHBr that's around 3.4 to 3.6, but an RCHBr, 2 electronegative elements attached, holy cow, that's going to be pulled even further downfield. So stand forewarned. You've got to keep an open mind when you're using your correlation chart. Guess what? It's not black and white. All right, let's look at some examples. So what do we got here? We have a propane, 1,2-dichloropropane, plain old-fashioned methyl group. They typically show up upfield around 1 part per million. This is pulled slightly to the left by virtue of the fact that there's a chlorine nearby. The CH2 with a chlorine attached, well, that's pulled far downfield. Again, this is an example of electronegativity. An electronegative element deshields, exposing those carbons and hydrogens to a stronger effective magnetic field. And then compare these two guys. All right, this is a methylene, this is a methine. They both have 1 chlorine attached to the carbon on which they're residing, but following that trend we talked about earlier, the methine is going to be further to the left, further downfield than the methylene. One more example. What the heck is this? Well, if you have your correlation chart in front of you, which, like I said, get close and comfortable with that correlation chart, you can look at it and say, well, these are probably hydrogens associated with an aromatic ring, because that's what shows up in the region of 7 to 8 parts per million. And this, well, it's downfield, relatively speaking, Maybe it's next to a bromine or a chlorine or an oxygen. Who knows? Well, this happens to be the NMR spectrum for methyl benzoate. So here is the 3 hydrogens on the methyl group from the methoxy, and the other 5 hydrogens on the aromatic ring show up downfield. Alright, so that is the electronegativity effect, and we certainly talked about the methyl, methylene, methine effect. What about, whoa, what's that other one? Magnetic what? It's easy to pronounce. All you have to do is look at this. It's pretty easy, right? And no T. And, well, that's pretty obvious. And I saw. This one's a bit dodgy, I'll admit. You're throwing a ball. You get rid of the H, tro. Anisotropy. Magnetic anisotropy. See? Not so difficult. Magnetic anisotropy? What's that all about? It's about this. It's about my cat toy. It's about that crazy circulation of electrons that we see, in this example, in an aromatic ring. Circulating electrons generate a magnetic moment. So here is my circulating pi electrons in my benzene ring. As they circulate, they generate their own internal magnetic field, as indicated by these blue lines. Well, the internal magnetic field is aligned such that it reinforces the external magnetic field of the magnet. So those poor hydrogens on the outskirts of benzene are getting blasted by kind of a double dose of magnetic field. So, wow, that's a super big gap, super big energy gap, and therefore their absorbance is way downfield in that realm of 7 to 8. That's a pretty good explanation when you consider that otherwise, it's really hard to explain why this would be so incredibly deshielded, because there's certainly nothing electronegative about the carbon upon which this hydrogen is residing. So magnetic anisotropy plays a big role in chemical shift, and I'm not going to go through all 3 examples just to keep this a little bit shorter. Just beware that there's bells and whistles, serious big time bells and whistles, and that's supposed to look like a whistle. Don't make any comments about that. Okay, bells and whistles. And the bell and whistle that we've already pointed out before is this one. Huge. I should blow a whistle right now. Oh, I guess I just did. That's an aromatic ring. Bingo. If it's between 7 and 8, you have this guy. You got other stuff, obviously. You got something here, you got something here. But these, aromatic ring. So that's, as I would like to say, screaming aromatic ring. Alright, this one's a lot more complicated. But what do I know about it? Well, the first thing I know about it is, oh, there's a molecular formula. Haha, what am I going to do with that? You know what you're going to do with that. You're going to figure out the units of unsaturation, and you're going to say 10 times 2 is 20. 20 plus 2 is 22. If it were fully saturated, it'd be 22. It's not. It's only got 12, so it's missing 10 hydrogens. This has 5 units of unsaturation, or the index of hydrogen deficiency is 5. An aromatic ring counts for 4. And I know I have an aromatic ring because look at all those signals between 7 and 8. All right, I'm going to wrap this one up because it's getting long enough, but let me just point out, when I'm looking at these things, I'm saying whatever this molecule is, it has 4 different sets of hydrogens. This is one set of homotopic hydrogens. This is another. This is a third. And the aromatic ones, they're kind of dodgy, but they're basically all in the same region. Okay, so I'm going to stop this. We'll pick it up in another little mini lecture that will be quite short, but this is enough for now. See ya.